So, we will be talking about the course on probability theory and its applications. Somehow when you utter the word probability to a layman, it does not sound very familiar, or one does not feel very comfortable with it, but my attempt in this course would be that at the end of the course you feel that you can understand what all goes behind computing the probability of an event. So, basically probability theory is estimating the possibility of outcome of an event. So, this word possibility, that what are the how possible, how probable the event is actually done by counting. And so, therefore, before I start giving you axioms of probability theory, I would like to begin with the basic concepts of counting, because that helps you in estimating the possibility of the occurrence of an event. And I will try to explain what we mean by an event and so on. So, as we go on, hopefully you will understand all these terms. So, let me just begin why. So, therefore, the first topic I am going to talk about is counting, and I will start with an example. So, suppose there is a small community which consists of 12 women and each of whom has 2 children. Now, if one woman and one of her children, so it has to be the pair, a woman and her child. So, if the pair has to be chosen as mother and child of the year, how many different choices are possible? So, let us just, it is a very simple way of counting. So, what I am saying here is that first experiment would be number of possibilities of the first experiment would be choosing the mother. Out of the 12 women, we choose one of the women as the mother of the year, and so the number of possible outcomes is 12, because there are 12 women and one of them will be appointed or chosen as the woman of the year. And then we will, the second experiment would be selecting one of her children as the child of the year. So, once you have chosen the mother of the year, then she has 2 children. So, only one of them can qualify to be the year of the child, child of the year. So, therefore, the possible outcomes are 2. So, then we say that the total number of choices is 24. So, I sort of broke up this event, I will call it event of choosing the mother and child of the year, by first saying that I will choose the mother and then one of her children would be chosen as the child of the year, right. So, therefore, the number of choices are 24, right. So, if now I want to sort of formulate this into the basic principle of counting, then the basic principle says that if there are 2 experiments to be performed, and experiment 1 results in any one of m possible outcomes. So, I have way of finding out that whatever my first experiment and the possible outcomes of that event are m. So, for example, here my first experiment was choosing the mother of the year, and since there are 12 women out of which I have to choose the mother of the year. So, there were 12 possible outcomes of this experiment. Any of the 12 women could have been chosen as the mother of the year. So, the first experiment results in m possible outcomes. Now, for each outcome of experiment 1, that means for each of the m possible outcomes here, then I want to know what are the possible outcomes of the second experiment. So, in that example, the mother had 2 children. So, it could only be one of the 2 children who could be chosen as the mother of the year. So, now here we will say that if for each outcome of experiment 1, there are n possible outcomes of experiment 2, then together there are mn possible outcomes of the 2 experiments, right. So, I hope this once you understand this basic principle of computing, of counting, then things become simple, because you have to first find out what are the possible outcomes, and then we will talk about when we define the concept of an event, then we will try to find out in how many ways a particular event can occur. So, here the total number of this thing are this. Now, if you want to generalize this concept of counting, so this will be generalized basic principle of counting, and here we will now say that suppose I have r experiments, which could be 1, 2, 3, whatever the number, and then again we will start saying the first experiment results in n1 possible outcomes. Okay. So, the first experiment results in n 1 possible outcomes. Now, for each possible n 1 outcomes of the first experiment, right, for each possible n 1 outcome of the first experiment, there are n 2 possible outcomes of the second experiment. Right. And then the third stage we will then count for each possible outcomes of the first two experiments, right, because two experiments have taken place. So, for each possible outcome of the first and the second, that means now you have n 1 possible outcomes of the first experiment, n 2 for each of the experiment outcome, here you have n 2 possible outcomes. So, total number of outcomes become n 1 n 2. Now, for each possible outcome of n 1 n 2, the third experiment the possible outcomes will be n 3 and so on. So, you will go on counting this, and therefore, by simple arithmetic you can see that the total number of possible outcomes would be n 1 into n 2 into n r. That means, at for each experiment whatever the possible outcomes, you will multiply them all. So, this gives you the generalized principle of computing. So, let us look up at this example 1.2. How many 8 place license plates are possible if first 4 places are to be occupied by letters and last 4 by numbers? That means, the first 4 can be any of the alphabet A, B, C, D. So, there were 26 choices for the first 4 places, and then for the last 4 have to be the numbers. So, which means they can be any of the digits 0, 1, 2 up to 9, right. So, now again as I quoted the generalized principle of counting. So, number of the first experiment would be choosing the first place of the license plate, right. So, then I have 26 choices because 26 alphabets are there. Then again for each of the alphabet I choose here, for each of the 26 alphabets I choose here, I can again choose the 26 alphabets again, right. If I have a letter A here for example, then I can choose any of the A, B, C, D 26 alphabets here. So, again the next outcome, that means the outcome for each outcome here, there are again 26 choices of the second experiment and so on. So, again for the third, that means now once I have chosen the first 2 alphabets here, then again for each of these outcomes 26 into 26, I can again choose in the third place any of the 26 alphabets. So, then the third choices, again the number of possible outcomes are the number of choices are 26, and the same argument goes for the fourth place. And similarly, for the numbers, if I have chosen one of the 10 numbers here, then again after having chosen all this, I can again choose any of the 10 numbers here, and then in the third place also any of the 10 numbers and so on. So, this will be the, and you can just see I have left a question mark for you to compute the number, it will be a big number. So, this many license plates can be there if you have this kind of arrangement that the first 4 places have to be occupied. So, it is a 8-letter license plate number, and so the first 4 places have to be occupied by alphabets and the last 4 by digits, right. Now, if I change the experiment and I say that repetition of letters and numbers is not permitted. So, the moment I say that once I have chosen a letter here, then the same letter will not be repeated here, here or here. So, then my way of counting will be this. Now, for the first place I have any of the 26 choices, any of the 26 letters can be chosen here, but once I have chosen a letter here, then that same letter is not permitted to be chosen here. So, now my choice for the second experiment for every possible outcome here goes down to 25, because whatever alphabet I have chosen here, I cannot choose it again. So, therefore, my choices here are 25, and once I have chosen an alphabet for the first place and the second place, 2 alphabets have been selected, then both these are not allowed to be chosen again. So, therefore, my choice for the third place would come down to 24. So, out of 26, 2 letters have been already chosen and they are not allowed to be chosen again. So, this choice will be 24, and then similarly at the fourth place I will be having a choice of 23. So, you can, if you just keep using this generalized principle of counting, which I enumerated some time ago, then you see this is how you will write down the possible outcomes. And similarly, for the numbers, for the first place I will have choice of 10, but once I choose a number here, then my choice is limited to 9, and after this again I can only choose out of the 8 which are not repeated, which have not been already chosen, and then similarly for the fourth place my choice will be left limited to 7 numbers which have not been repeated. So, this is the kind of, so the generalized principle of counting helps you to come out with the possible number of outcomes of an experiment, right, or event here what you want to say, because this was as I am counting, I am saying that this is 8 experiments, choice of each letter for each place of the license plate and a choice of a number I counted as experiments. So, I had 8 experiments here and used the generalized principle of counting to find out the possible number of outcomes, right. Now, another possible, another way of counting is done by through permutations and combinations, and let me now here try to explain the difference between permutations and combinations. So, here let us say we have collection of 3 novels, and so I will just say that the authors are A, B and C, then 2 mathematics books, and again I will distinguish them or differentiate them by the authors and call the authors as D and E, and 1 physics book I will call the author as P. Okay. So, there are 6 books, and since I am distinguishing the books by the authors, so it is not just novels, I am saying that the I mean the authors are A, B and C. So, they are different novels I am distinguishing. Similarly, I am differentiating between the 2 mathematics novels, and of course, there is 1 physics book. So, the question is how many arrangements are possible if the books are to be distinguished by the authors. So, I am wanting to make arrangements of these books, and arrangements would be differentiated because I will be referring to the books by the authors. So, it is not just novels or a mathematics book. So, therefore, possible arrangements, now here again let us just say that we are okay, right. So, here that means in the first place if we now count the thing, then that means I can say that there are 6 places, right. So, now the choice for the first place, that means I am just arranging the books like this in a row suppose. So, the choice for the first place would be any of the 6 books, right, because I am differentiating the books by the authors. So, therefore, for the first place the choice is 6 books. Once a book is placed here, then there will be 5 more left, right. And again, so therefore, out of the 6 experiments, I am just saying that what are the possible outcomes. So, once I have chosen 2 books here, then I am left with picking out the book for the third place from among the remaining 4 books, and then 3, 2 and 1. So, the total number is 6 factorial, which is 720. Right. Now, these 720 arrangements are known as permutations of the 6 books, and the permutation word is essentially saying that the permutations are the ordered arrangements of the books. Now, by order I mean that if I am writing, say for example, ordered arrangement I want to say, ordered arrangement. So, if I am writing here, say it could be that I have chosen all the 3 novels here, right, and then of course, let us say mathematics books you have D and E. So, maybe you have this and U, right. Now, if I have the order B arrangement BAC EDP, then you see this arrangement is different from this, because now here the second author, if you call the book by B as the second novel, then the second novel is occupying the first place, and this is the first the novel by the first author is occupying the second place. So, here the arrangement, and therefore, this order is also considered here in this arrangement, and therefore, I will say that this is different from this order, or this arrangement is different from this order. that arrangement BAC EDP. Okay. So, this is the idea that your 720 permutations are the ordered arrangements of the 6 books, and so how you place them depends on that means I am distinguishing between which author is occupying the first place, which author is occupying the second place, and so on. So, therefore, this way it will be 720, but if you do not distinguish between the authors, that means I just treat the 3 novels as novels, and in that case this and this arrangement would be the same, right. And in fact, you can see how many possible arrangements. See, I can have here CAB EDP. Now, you can tell me 3 more, because these 3 letters A, B, C themselves I can arrange in 3 factorial ways. That will be 6 ways I can arrange these 3, and therefore, all those arrangements, once if I do not consider do not distinguish between the 3 novels by the authors, as long as they are just novels, then that arrangement, all those 6 arrangements will be counted as one arrangement. So, when we are looking at the arrangement of the books, the novels, 3 novels, 2 maths books and 1 physics book. So, once we do not worry about the differentiating the books with respect to the authors. In that case, you see, as I tried to show you, that the 3 novels, since they will not be distinguished by the authors. So, then for every arrangement in which only the arrangement of the authors has been changed, the other books remain the same. In that case, 6 of those arrangements will amount to one arrangement, because the 3 novels can be arranged in 6 different ways, and if I leave the maths books and the physics book intact, then all 6 arrangements in which only the arrangements of the novels have been changed, then those 6 arrangements will amount to one arrangement. And similarly, corresponding to each of those, if I leave everything intact and only disturb the arrangement of the maths books, then since I am not differentiating between the authors, those arrangements will not be different, because the 2 maths books, whether the author D or E, whichever comes first, does not matter to me. So, in that case I will then divide. So, that means, when I am counting the arrangement where the order is not important, then that comes out to be 6 factorial was the arrangement, total number of arrangements where the order was important. But if I do not care about the order, or that means I do not distinguish between the authors, in that case the arrangements will become 60. So, this is what now I am trying to come to. So, in the permutations, the order was important, and then I said total number of permutations, that means that the order of the objects was also being considered, right. So, now the general principle that I am trying to enunciate, that in general number of arrangements of n objects where n1 are alike, n2 are alike and n are alike, That means, there are only are different kinds of objects, and since so therefore, surely here n1 plus n2 plus nr adds up to n, right. So, you have n objects, but n1 of them are the same, then n2 are alike, and similarly nr of them are alike. And in that case, when I am wanting to arrange the n objects, then the total number of objects would be, because n factorial would be the arrangements of n objects when I am distinguishing between each of them, right, whatever the way of distinguishing the objects, whatever it is. So, that was the total arrangement. But since, as I tried to show you through this example of arranging the books, that if n1 are alike, then those n1 can be arranged in n1 factorial ways, and they will amount to the same arrangement, because I am not differentiating between the order. So, therefore, I will divide this total number of arrangements here by n1 factorial, n2 factorial and nr factorial. So, that will give me the total number of. So, that becomes the number of combinations, where that means, the arrangements where the order is not important would be the total number of combinations. Now, let us look at this example. So, a tennis tournament has 9 competitors. Okay. Okay. So, and then 3 from India, 2 from Japan and 4 from Malaysia. Now, if the results of the tournament are announced by nationalities of the players, in the order in which they are placed. So, it is not, you are not distinguishing the players by their names, only their nationality is being considered. In that case, 3 from India would be just 3 Indians, and it does not matter which one gets the first position, third position, or whatever it is. So, here it will be just all the 3 players would be considered as players from India. So, another way of looking at it is that you can think of these 3 people as one entity, because they are just representing the same country. So, similarly 2 from Japan would be just distinguished by their nationality and not by their names, and from Malaysia. So, therefore, if you want to now find out the how many such lists are possible, that means what is the arrangement of the positions that these 3 the players from 3 nationalities occupy in your list, first, second, third, up to there will be 9 positions. So, then the total number of lists that you can have would be 9 factorial. So, 9 is the total number of players, and if I was going to distinguish them by the names, in that case there would have been 9 factorial arrangements of the way in which the order in which players would occupy a position in the tournament, but since we are not considering the names, we are only considering the nationalities. So, for example, we will then divide this number by 3 factorial, 4 factorial and 2 factorial to get the total number of lists. Okay. So, the 3 Indians can occupy any of the positions, and they will be the same. So, that means there are 6 lists in which if 3 Indians were occupying different positions, in the sense that I just rearrange the positions that are that means 3 Indians, if they just appear, see, suppose you consider the first position, second, third, fourth, fifth, sixth, seventh, eighth, ninth, and same thing here. So, if this was Indian, this is an Indian, and let us say this is an Indian, right. Now, whatever the 3 names, if I see, if you had a name here, say Indian 1, Indian 2 and Indian 3, then I can have Indian 2 here, Indian 1 here, Indian 3 here, and this way you can go on, right, Indian 2, Indian 3, Indian 1, and just see that you can write, you can rearrange these 3 in 6 possible ways. So, other arrangements remain the same, but if these 3 I can arrange in 6 different ways, but for me they are the same, because in my list it will appear as I. So, this will not be there, right. So, all these arrangements will be the same. And so, all these 6 arrangements will amount to the same. Therefore, I am dividing this number by 3 factorial, and similarly for the 2 from here in this case here, because that was the example for the books. So, here I am dividing this number by 3 factorial, 4 factorial and 2 factorial to get the possible number of lists. So, just trying to make the concept of counting clear, so that you can then when you have to compute the possibility of the occurrence of an event, all these things will come in handy. Okay. So, now again I am trying to enunciate this principle that if you have a collection of n objects, in how many ways can we select r objects? That is again the same thing, because you can say that you can put the n objects in a row and then you are picking up r out of them. So, that is a different arrangement. There is another way of saying the same thing, right. So, here by our principle of counting, when you can say that you have arranged all these n objects in a row and then you are picking up one of them. So, then for the first place, that means when I want to pick up r objects from this list of n objects, the first object, there are n possible ways of selecting the first. So, we are counting the same thing again by a different way. So, here you have n ways of selecting the first object. Then since you have already selected the first object, you are left with now n minus 1 ways of selecting the second object, right. And similarly, it goes on depleting, and finally, for the rth object that you want to choose, you are left with n minus r plus 1, because you have already selected r minus 1 objects. So, n minus r minus 1, this is the number. So, this many ways you can select the rth object, right. Now, since it does not matter again, because I am not distinguishing between the r objects, that means the order is not important. Once you see out of these n objects, I have collected r objects. So, it does not matter which one came out first, which one came out second, as long as the set of objects is the same. So, that means my way of selecting may have been, because I picked, when I picked up the first object, that counted as the first object, second and so on. But then finally, what I have with me is the set of R objects, and in that set, the third or the fourth object could have been selected first, does not matter, right. So, therefore, what we are saying is, now you have n minus r plus 1. So, that means the total number, I should have written the number here, let me write somewhere here. So, the order is, when the order is immaterial, I am saying that this is, let me just write it here. So, that means what I am saying is that the first object I could pick in any of the n ways, then for the second object to pick up, I had only n minus 1 choices available with me, and so on up to n minus r plus 1, right. So, this number, and since what we are saying is that it was not important the order in which the R objects were selected, it is only the final subset of R objects that I have with me. So, therefore, I will divide this by R factorial, and so you can write this number. You see, if you have up to this number you can write as n factorial divided by R factorial n minus R factorial. So, this is the final. So, that means this is the number of combinations I can have, because by selecting R objects I can call an arrangement that was here, that means the n objects that I have, I pick up R, I put them first, and then the remaining n minus R. So, essentially the R objects that you pick, it does not matter in what order you pick. So, therefore, the total number of ways in which I can arrange my n objects gets divided by R factorial, and obviously, the last n minus R objects also, the order is not important, because finally, you have divided these n objects into R and n minus R, right. So, it is simply which R objects get selected, it does not matter in what order they got selected. So, therefore, the total number of ways in which you can pick up R objects from n objects would again be given by this number, and normally we say n choose R. This is the notation for this number, n factorial divided by R factorial n minus R factorial. So, this is n choose R. So, again let us take up an example. So, a jury of 7 is to be formed from a group of 30 people. How many different juries can be formed? So, just carry over the what we discussed just now. So, there are 30 people, and you have to pick up 7 people from this set of 30 people, which will form a jury, right. And so, you want to know how many, the question is how many different juries can be formed. So, this is like we discussed n objects, you want to pick up R objects from there, and how many ways are there, how many possible combinations are there, that is what we are looking at. So, obviously, you can see that the number of juries would be, so first person in the set can be chosen out of the 30 people. Then once you have chosen that person, you are left with 29 choices. Then again after these two, you are left with 28 and so on. So, this number is 24. And now, what we are saying is that it was not at all important as to when we have selected the 7 people, since this is a subset of 7 people, it does not matter which one of them got selected first. So, the order is not important, it is only that finally, I have this subset of 7 people. So, therefore, the 7 we will have to divide by 7 factorial to get the possible number of juries, because this 7th set of people that you are forming the jury, you are not looking at when the first in what order they got selected, that is not important, right. That is what I am emphasizing again and again, that here the order of selection is not important. It is just that we want this subset of 7 people, and therefore, this will be the total number of arrangements. And so, here with this number you can write, because this is up to 24. Remember, this is n minus r plus 1. So, here your n is 30 and your r is 7. So, when you want to divide from 36, you are left with 24. And so, this is the total number. If it was important as to in what order the people got selected for the jury. Since it is not important, it is not being considered, it is immaterial. So, therefore, I divide by 7 factorial, and this number can be written as 30 factorial divided by 7 factorial into 23 factorial, which by our notation is 30 choose 7. Okay. Now, in case the group of 30 consists of 10 women and 20 men, and if it is required that 2 women and 5 men should form the jury. So, now we are saying that out of the 10 women 2 must get selected, and out of the 20 men 5 men should get selected to form the jury. So, in that case the number of groups of women that you can form out of by choosing 2 out of 10, this will be 10 choose 2. Here again the order is not important, I just want to select a subset of 2 people, 2 women from out of the 10. So, that will be a total number of ways in which I can select the 2 women from the 10 women, and similarly I can 20 choose 5 is the number of ways in which I can select 5 men from the set of 20 men, and so the total number would be, because for each subset that I choose here of women, there will be this many. So, I am now using here my generalized principle of counting, and so the total number of ways in which I can the number of juries of 2 women and 5 men can be formed is this. Okay. So, just through examples I am trying to make the concept clear, and now let us see that you can, all of you have used binomial theorem, and you know that if you want to if you want to expand this number x plus y raised to n, then the formula is n choose k, x raised to k, y raised to n minus k, and you have done it by induction and so on, the proof. Now, let me give you this combinatorial proof of binomial theorem using this concept of counting that we have learnt here. We can use this and show that the expansion of this term can be written in this way. And so, let me consider the product x 1 plus y 1 into x 2 plus y. So, there are n terms here, right. Now, when I am multiplying, each term here final in the product would be consisting of n factors, a factor of n of the xi's and yj's. That means, each term of this product will contain, when you count the number of xi's and yj's, that total number would be n, because you have n factors, right. But certainly, in any factor, when you look at the xi's and yj's, if an xi appears, then the same index will not be for y, because you see x 1 and y 1 are in the same term here. So, therefore, when I multiply, either I will be multiplying x 1 by the other terms, and so then y 1 will not appear in that, right. So, therefore, in any product, the xi's and yj's that you have, if an xi appears, the corresponding yi will not appear in that product, right. So, in other words, what am I saying? That any term of this product which will contain, let us say, k of the xi's and then the remaining n minus k of the yj's would be such that, so you are choosing essentially each term here would contain, let us say, when I am looking at the term containing only k of the xi's, and so remaining n minus k are yj's. So, then how many ways can be there? How many such products can be there, in which, so this is containing each term in this product has n factors containing xi's and yj's. So, then if I am looking at all the terms which contain k of the xi's, right, then that means I am out of the x 1, x 2, x n, these n x's I am choosing k of the xi's, right. And then of course, the moment I choose my k xi's, then the yj's got the n minus k yj's get selected automatically, because the ones which are not appearing in my x 1, x 2, the product of xi's that I have taken, the remaining indices will go to the yj's, right. So, here that means, and that ways the way of choosing k xi's out of the n xi's x 1, x 2, x n is n choose k, right. So, therefore, the number of terms which contain k of the xi's is this many terms. And so, this whole product, either what will happen, say for example, if you look at the product y 1, y 2, y n, no xi appears. So, the k can vary from 0 to n. The terms will contain either 0 xi's, then 1 xi, 2 xi's and so on. So, you want to add up all such things. So, you want counting the total number of terms in this product, and that total number will be given by summing up n choose k from 0 to n, and when you choose like this, then that means your k of the xi's are here and n minus k are here, you are adding up, right. So, this thing then I put xi equal to x for all I and yj equal to y for all j. So, in that case your k of the xi's that you took from here, they all become equal to x. So, x raised to k, y raised to n minus k. So, then therefore, this product, and when you put the xi's together equal yi's all together, then this whole product coincides with this, and so you have a nice way of proving the binomial theorem. Okay. Now, an immediate application of this is that if you want to count, you have n objects and you want to count how many subsets can be there of these n objects. And of course, the empty set also we consider as a subset, that means nothing gets chosen from the n objects. So, you can have subsets consisting the empty set, then you can have subsets consisting of only one element from one object from these n objects, subsets containing 2 objects, 3 objects and so on. So, if you want to count the total number of subsets that you can form of these n objects, then since I told you that nck gives you the number of subsets of size k, right. And so, you want to count this number nck from k varying from 0 to n, and which if you look at this expansion here, essentially you are putting x equal to 1 and y equal to 1. So, that this all becomes 1, and so you are summing up. So, on this side when you put x equal to 1 and y equal to 1, this reduces to 2 raised to n. So, the total number of subsets, this is another nice way of counting the number of subsets that you can form given n objects. So, extending this concept that I just enumerated for you for the binomial theorem, now we can take over go up to multinomial coefficients. So, this is a set of n distinct objects is to be divided into r distinct groups of sizes n 1, n 2, n r. For the binomial theorem, r was 2. So, now it is n 1 plus n 1, n 2, n r, where of course, all the n i's add up to n. So, I am dividing these n objects into r sub groups, and the size of each group, the first subgroup is n 1, size of the second group is n 2 and so on, right. So, then using the same principle, I want to choose from n 1 possible groups. So, the number of possible groups of size n 1 is n 1 and n choose n 1, right. Or you also write this as actually this is also written as n c n 1. So, combinations. So, n 1 combination, that means you want to choose n 1 objects out of n. So, what are the possible number of ways? So, any of these notations is acceptable, fine. So, the first group will be the number of groups of sizes n 1 would be n choose n 1. Then since I have already chosen n 1 objects out of n, so then I want to choose the second set of objects n 2 consisting of the set of objects must be n 2 in size, and then so out of n minus n 1 I want to choose n 2. So, for each group of size n 1, the number of choices of the second group is n minus n 1 choose n 2, right. And so, you extend this concept, and so finally, the last choice would be, because now you will be left with n minus n 1 minus n 2 minus n r minus 1, r minus 1 subsets or subgroups have already been chosen. So, then this many you are left, and out of this you want to choose n r objects. So, again the number of possible ways is n minus n 1 n 2 minus n r minus 1 choose n r, right. And so, we will say that the total number of groups is the product of all these, right. And so, by a notation, this will be the first one would be n factorial divided by n 1 factorial n minus n 1 factorial. Then the second one would be n minus n 1 factorial divided by n 2 factorial n minus n 1 minus n 2 factorial and so on. So, if you see that this will be my total expression, and then the terms cancel out, because you have n minus n 1 factorial here and this is n minus n 1 factorial. So, it cancels out. So, these terms will cancel out in pairs, and so in the denominator you will be left with n 1 factorial, n 2 factorial, n 3 factorial up to n r factorial. And this is what again what we are saying is that we are deciding whatever objects we are putting in one group, we are saying they are all alike. The same principle you are using, and so their arrangements will not matter in whatever way you choose, in whatever order you choose is immaterial. So, therefore, again I can arrange my possible objects n objects in n factorial ways, but since I am grouping them into r different subgroups, and each group the number of objects is we are not differentiating between the objects in one group. So, then the total number of ways would be n factorial divided by n 1 factorial, n 2 factorial and n r factorial, right. And now, this helps us to expand. For example, this gives the multinomial theorem that if you want to expand x 1 plus x 2 plus x 3 plus x r raised to n, then it will be, because remember in this product, just as I showed you for the binomial theorem, you want to choose. So, because each product here will consist of some powers of x 1, some powers of x 2, some powers of x 3 and x r. And so, here I am now saying that these n 1, n 2, n r will vary from, because every product here will contain 0 x 1, 1 x 1, 2 x 2, 2 x 1 and so on, and different. That means, whatever the powers, each term here you can see in the product, these terms will appear, and so your n 1 plus n 2 plus n r must be, because each term, this is raised to n. So, each term in this expansion will contain n xi's together. So, that means, you add up the indices of x 1, x 2, x r, they should add up to n, and that is what is given by this, right. So, therefore, using this concept, this is how you can write the expansion, right. And if you look at this example, where x 1 plus x 2 plus x 3 raised to 3, then you see I can choose my n 1 to be 3. So, that means, this subset contains just the component, the powers of x 1, powers of x 2 and x 3 are missing here, right. So, therefore, the expansion, this is 3, 3, 0, 0, x 1 raised to 3. Then here again you are choosing a subset from 3, which consists only of powers of x 2. So, 0, 3, 0, and so this will be x 2, 3, right. So, I showed you the the idea behind this, and then now I am using it repeatedly to say that how you can write the expansion of this, right. And so, therefore, you can see that the way I can choose my numbers n 1, n 2, n r such that they add up to n. So, in the case when you have your r is 3 and your n is also 3, so then these numbers must add up to 3. Right, you are dividing your number 3 in 3 possible ways, so that they add up to 3. So, here these are the possible, right, and the final thing is 3 1 1 1, when each x 1 x 2 x 3 has only power 1. So, this is the expansion, and now in the assigned exercise sheet that we will just show you, I am asking you how many terms are there in the multinomial expansion. And remember, because which is actually counting the number of subsets, right here, essentially you are counting the number of subsets that you can have, like you have r, this thing here, x 1, x 2, x 3, x r. So, essentially my question is, how many terms are there in this expansion? And so, I have already discussed this case with you for the binomial, how I used for answering the number of subsets of total number of subsets of n objects. So, here you have to use the same concept and tell me how many terms are there in this multinomial expansion. Okay. So, let me just show you the discuss the exercise sheet. Question 1 is straightforward. 18 workers are to be assigned to 18 different jobs. So, the important part here is that each job is different from the others, and therefore, this will be an ordered arrangement of the 18 workers. So, you can write down how many possible assignments are possible. That means, an assignment would mean that you assign one particular worker to a particular job. So, then in how many ways can you do this? This is the idea here, right. Now, consider a group of 25 people. If everyone shakes hands with everyone else, how many handshakes take place? So, that means that if a person shakes hands with another person, then both have shaken hands with each other. So, just keep that in mind and you can immediately write down what the answer will be for number 2. Now, here in question 3, 4 separate awards. It can be somebody getting the highest marks, the highest cumulative performance index, best sportsman, leadership quality, etc. So, you can have 4 different awards given to these students, and the idea is to select from a class of 36 students who can be given this award. Now, in case a student can receive any number of awards, then it will be a different number of arrangements that you can have, or different ways in which the 4 awards can be given to a student or more than one student. But in number 1, the condition is that the student can receive any number of awards. So, you have to do a counting in that way. So, in number 2, we say each student can receive at most 1 award. So, that means either a student receives an award or a student does not receive an award. So, this is the way you have to count. Now, in question 4 is interesting. Using combinatorial argument, prove that n choose r, that means selecting r items from n items is equal to selecting r minus 1 items from n minus 1 plus selecting r items from n minus 1 items. So, you can, if you write down the expression for n minus 1 choose r minus 1 and plus n minus 1 choose r, you can show that these two add up to n choose r, right. But I want you to give a combinatorial argument, and you can see here in the first term it says n minus 1 choose r minus 1. That means, I am keeping away one particular object or item from the n that are there, then I am selecting r minus 1. So, that means, the first set of numbers n minus 1 choose r minus 1 gives you the number of ways in which you can pick up r minus 1 objects from n minus 1 when a particular object is been selected. So, when you add that to this selected group, then it will become r objects from n objects. Now, the second one says that n minus 1 choose r. That means, that particular, see, the thing is that either the particular object or item that you have picked is either there in a collection of r objects or it is not there. So, the first case says that yes, it is going to be in that collection of r objects. So, once you add it to the set of r minus 1 objects that you have selected, then it becomes r. Now, in the second one, what you are saying is this is a set of selections in which that particular object does not appear. So, you have separated that object, and from the remaining n minus 1 you are choosing r. So, this is the kind of combinatorial argument you are giving to prove the identity. And so, you see I have already shown you that you can, by combinatorial arguments, you can you prove the binomial theorem. Now, similarly, you can try to prove a number of such identities through combinatorial arguments. Okay. Then question 5 we have already discussed, in how many ways can r objects be selected from a set of n objects if the order of selection is also to be considered, right. So, question 6, one delegate each from 10 countries that include delegates from India, Pakistan, Bangladesh and Sri Lanka are to be seated in a row. Okay. So, the arrangement has to be in a row. Now, delegates from India and Sri Lanka are to be seated next to each other, and delegates from Bangladesh and Pakistan are not to be seated together. How many seating arrangements are possible? So, the idea here is that you have 10 different positions. People are sitting in a row, and you want people delegates from India and Sri Lanka to be seated together, right, which means that I can treat those two as one person. In that case, it will be 9 people then who have to be arranged, because delegate from India and delegate from Sri Lanka have to be together. So, that means the total arrangements is 9 factorial, but since the people are sitting in a row, that means the arrangement that first the Indian delegate is sitting and then the Sri Lankan, or the Sri Lankan delegate is sitting first and then the Indian. So, this will count as 2 different arrangements, and therefore, the total number of arrangements would be 2 into 9 factorial, in which the delegates from India and Sri Lanka are together. Now, you do not want people delegates from Bangladesh and Pakistan to be sitting together. So, now again consider the situation when they are sitting together. So, we will subtract the number of. So, in that case if you now look at the arrangements in which delegates from India and Sri Lanka are together and delegates from Bangladesh and Pakistan are together, then you know you will have 8 different positions to arrange, because these 2 delegates will be together, that means that they can be treated as one person, right, and therefore, it will be total number of arrangements would be 8 factorial, but then again you have to, it can be 2 possible, you know, like as I told you, the arrangement can be India Sri Lanka or Sri Lanka India. Similarly, it can be Bangladesh Pakistan, Pakistan Bangladesh. So, therefore, essentially you will be subtracting from 2 into 9 factorial the number of arrangements in which all the 4 delegates from Bangladesh and Pakistan are together and delegates from India and Sri Lanka are together. So, that will be 2 square into 8 factorial. And so, you subtract this number from 2 into 9 factorial, that should give you the required number of people, number of ways in which you can have the required arrangement. How many terms are there in the multinomial expansion of x 1 plus x 2 plus x r raised to n? So, here again I am wanting you to do this exercise. See, the whole idea, the way I explained to you this expansion was that you are essentially dividing your number n into r smaller numbers n 1, n 2, n r, such that they sum up to n. So, in how many ways can you partition this set of n numbers into r subsets, so that they all add up to n? This is the whole idea. And so, you will see that from this identity x 1 plus x 2 plus x r raised to n, you have to put all these x 1, x 2, x r equal to 1, and so you get r raised to n is equal to the number of terms that appear in the expansion, multinomial expansion of this term, right. Then finally, a total of 6 gifts are to be distributed among 9 children, so that no child receives more than 1 gift. This is exactly the same as you know part 2 of 3, right, because here also we said that no student should get more than 1 award, should get at most 1 award, and so here also we are saying that a total of 6 gifts are to be distributed among 9 children, so that no child receives more than 1 gift. Okay.